Okay, here we go. So we're doing number 48. This is problem number 48 from chapter 14, and it's part E. Okay, part E. So they're asking us for the pH at the half equivalence point, and it's a titration between sodium hydroxide and hydroiodic acid. So it's a strong base, strong acid titration. And so we're going to create our little BAA table here. When you write the net ionic equation for this, hydroiodic acid is going to be completely ionized, 100% dissociated, and the iodide ion is just a spectator. Sodium hydroxide, same thing, completely ionized, and sodium's a spectator. So the net is simply H plus from the acid reacting with hydroxide from the base, and that goes to make water. So that's really all it is. Now, in a BAA table, typically we use moles, okay? And so using it tells us that we're using 37 mils of 0.1988 molar HI acid. And so, you just multiply molarity times volume in liters, and that'll give you the number of moles. And I'm going to, because these numbers are small, I'm going to use millimoles, okay? So when you do the multiplication, you get 7.356, okay, 7.356, and that's millimoles, okay? So that's how much acid is sitting there in the beaker. And then if you begin titrating with the sodium hydroxide, half equivalence is when you've dispensed enough sodium hydroxide such that you've delivered half this many moles to the beaker, and you've essentially reacted half of the H plus, and that point occurs when you have dispensed 3.678 millimoles. Okay. Now over here, let me make a little calculation area over here, and we'll do this in maybe we'll do this in green. So as we know, the number of moles of hydroxide that we dispense is equal to the molarity of the hydroxide solution times the volume of the hydroxide, right? So what we want to know is, given the molarity of the solution, and given the fact that we want to deliver half, this many millimoles to neutralize half of this H plus, we can calculate the volume required by simply solving for volume, right? So the volume of hydroxide is going to be equal to NOH minus divided by molarity OH minus. And when we substitute in, that's simply going to be, now I'm going to go back to moles, okay, from millimoles, 3, 6, 7, 8 moles divided by the molarity of the hydroxide solution, which is 0.2128, and that's the molarity. I'm going to unpack the molarity into moles per liter so we can see that we're going to end up with liters. And when you do that calculation, the volume that we need of the hydroxide is 17 in milliliters, okay, 17.28 milliliters. Okay, that's volume of hydroxide solution. Okay, so I'm going to come over here. I'm going to make another row, and I'm going to call this the volume. Okay, so this is the volume section. Okay, so to start, when we just had the acid at the very beginning of the titration, it tells us that we had 37.00 mils, okay? And now we know that at half equivalence, when we dispense half as many moles of OH minus as we had of H plus, that's going to take 17.28 milliliters, right? So milliliters. Oh, sorry about my pen here. Okay, and that tells us something very important, which is, the total volume of the solution at half equivalence. Okay, so now let's see. At that point, all of the OH minus will have reacted with the H plus. So if you look at at this reaction in terms of stoichiometry, the H plus is the excess reactant when you've only put in one equivalent, or I'm sorry, half equivalence of OH minus. So OH minus is, in a sense, the limiting reactant here. And so you're going to have left over, you'll have 0 hydroxide left over at that point. It's all been reacted by H plus, and you'll have this many millimoles of H plus, okay? And that many millimoles of H plus is sitting in a total volume equal to the sum of these two volumes, okay? So what we, to kind of keep our eye on the ball, what we really want is pH, right? And to get to pH, we need to know the H plus concentration. And to know that, we need to know the number of moles of H plus in the volume, okay, like the total volume. Okay, so now we've got all that information. So I'm going to go over here and let's do that in green again. I like green. All right, so H plus, so the number of moles of H plus is equal to, now I'm going to go back to just regular moles, 0.003678 moles over the total volume. So if you add these together and put that in terms of liters, this would be 54.28 milliliters, which is 0.05428 liters. And when you do that calculation, you should get 0.06776, and that's moles per liter. Okay, now this is very important. This is our H plus concentration, and now all we got to do is take the negative log of this, and I'm going to kind of go over here. When you do that, I get 1.169. That's what I get for pH. Now I notice that the book in the answers has a value of 1.19, which is different from what I get. And the only thing I can figure is, well, I mean, there's two questions I have. The data given in the problem is everything's to 4 sig figs. And so, if you carefully carry through 4 sig figs through this, I'm not quite sure where things get dropped. And it seems like, by rights we should have 4. I should be keeping one more digit in the pH. I should be keeping 4 decimal places because I've got 4 sig figs here. That's one thing. The second thing is, our answers, even if you round to 2 decimal places, that would give me 1.17, which is a little different from 1.19. I'm not sure why we're off a little bit. They may have rounded to fewer digits earlier in the process, but I think within rounding and certainly with an experimental error, these two numbers are really the same thing. Okay. So anyway, I hope that helps, and you guys just send me an email if there's anything else I can flesh out here for you. Okay, thanks.